Recording in progress.
Okay, so let's get started. So the first part is the neural network. Sometimes people also calls it as artificial neural network, and sometimes even multi-layer neural network, even sometimes multi-layer perceptron. Different names though, but everything basically comes down to neural network, right? So the first thing that I just want to bring it up, what are there are few. Okay, yeah, no problem. So what are the different functions we can do using neural network? Yeah, so that's fine. I think I'll keep it pretty simple today, because yeah, the strength is pretty demotivating. So basically we can do function approximation, right? So when we say function approximation, so that basically we can do the two tasks. The first one is basically continuous functions, right? So continuous functions, and then the second thing we can do is the discrete function approximation. So continuous function is basically kind of regression tasks, right? So kind of regression task. So for example, what is the price of a home coming month, something like that. So if it's a discrete, then it's basically a classification, right? So classification is classification, right? So basically we do kind of whether this image is a tiger or a cat or something like that. So these are the things we can do using the neural network. And when it comes to a basic what's the minimum number of hidden layers we require for a function approximation? Basically, at least we need one. So right, so that's the minimum thing. And the third point is basically when we say a neural network basically consists of neurons, right? So when we say one neuron, it basically is summation, which with some kind of nonlinear activation function, and that gives the output. And this can take all the inputs, right? X1 to Xn, and this Xn basically is from the real with the dimension n, and we can add the bias as well, right? So that's the basics about the neural network. And I actually plan to teach backpropagation algorithm, because that was there even in the lab. And whenever you claim you know anything in the machine learning, especially with the neural network, you basically have to be very eloquent when it comes to backpropagation, or else you can't claim that you know the neural network, right? So I thought to share my points regarding the backpropagation algorithm and how to write the backpropagation algorithm. Anyway, so let's take one simple network where this is the input, and I would say this is first neuron, okay, and then this is the second neuron, right? So why I say net one is basically the terminology used in this particular course. It's up to you that you can use anything else. It depends on the notations that you want to use, and you can really call it anything else. It depends. So and the final or the output neuron, I would call it as net3 and y3. So if I just maximize this, so that basically is net1 is given to y1. Y1 is a kind of nonlinearity function, and this is basically is a summation. That's what I just explained here, right? So this is I'm trying to call it as net1. Okay, so there's a question. No, it's, yeah. I mean, if you would call it J and then gives the values for the J, that's fine. But I'm just calling it as net 1 and net 2, but you can call it as net J, where J takes the value 1 and 2, something like that. It's up to you. Okay, so X1, and this is how the connection goes to, and this is just one hidden layer, right? This is just one hidden layer, and this is the output layer, and this is the input layer, right? And I just want to call the output as Z, okay? But you should be knowing that Y2 is nothing but Z, right? Y2 is nothing but Z in this case. But I just want to call that, call the output as Z. So now, even before going to write the backpropagation algorithm, we just have to write the forward propagation. So before forward propagation, we just have to decide what kind of cost function we're going to use. And I want to use a pretty simple cost function for this case, just to make the thing simple to understand the backpropagation. So I just want to use a square error. So T is the target value and Z is the output value. So T is basically the truth value, right? So this is what the error function I just want to use. And then the nonlinear function, I want to use the all pass activation function. Okay. So all pass activation function is basically is kind of short circuit. It just pass everything, whatever it gets, right? So here it basically means there is a short circuit. There's nothing like, there's no nonlinear function in this case, right? So yeah, so that's the meaning of all pass function. The reason that I'm taking all pass function is basically to make it simple to understand in the first go. So before getting into forward propagation, I just want to introduce the concept that the backpropagation update rule using gradient descent, right? So in that, what happens is if you take any parameter, so old parameter, we just have to update this old parameter with a newer value of gradient descent algorithm, right? So that what basically is. So it's not old. So this is new, right? So new parameter basically with the old parameter, and then minus either the, I don't want to get into the derivation of this particular equation, but you guys have known this in your lab 3, because you guys just did the multi-layer neural network, and in that you guys use this, right? So what does this mean is basically, okay, I just want to introduce the weight notation. So I just want to call this W11, the weight value between X1 and the first neuron. And I want to introduce the bias as well, just to make sure. Okay, and this, I want to call this as W21 from X2 to neuron 1. So this first one is basically indicates the input, and the second one indicates the index for the neuron. So these notations, you don't have to worry too much. These notations, I'm just trying to introduce them, but if anything is given in the final exam, it should be explicitly mentioned what is what. Okay, but you just have to be very sure on the concept so that you can write the backpropagation update rule for any problem. So I got it. So this WW1, I just want to call this as a weight value between the neuron 1 and the neuron 3. Again, similarly, W2 is the weight value between neuron 2 and neuron 3. So for example, what I mean by this particular equation is if I want to update the rule, if I want to update the weight value of W11, so that basically is W11 minus eta dou Fe divided by dou W11, right? So that's what I mean to say, the update rule. Okay, so let's write the forward propagation. Right, so for propagation, first we need to see, so let's write it from the first neuron. So that's the net1. So net1 is basically W11 x1 plus W21 x2 plus B1, right? So this I think you guys are clear, right? Yeah. And then, so we have Y1. Y1 is basically activation function acted upon the net1. So Y f of net1. So in this case, the activation function is all pass function, right? So whatever the input comes in, it just passes the output. So it looks like something like this. So whatever it comes, even the negative, positive value, it just passes through. So that's the forward propagation for the neuron 1. And then let's write it for net 2. So net 2 is basically W12 x1 plus W22 x2 plus B2, right? And then Y2 is basically f of net 2, right? So till here, I don't think any issues. And then we will write the forward propagation for the last neuron, that's net 3, that's equal to W1 and multiplied by Y1, right? Plus W2 Y2 plus, is there a bias? Oh, so there's no bias. So we don't have B3, right? And then finally, what's the Y? Oh, this is Y3. Oh, my tab is stuck. Okay, came back. So this is Y3. Okay, so Y3 is equal to f of net 3, right? So this is the forward propagation, and then finally, just Z is nothing but Y3, right? But that's not required. That's not required. But I'm introducing Z because I'm calling this error function with a Z. So if I call this as t minus Y3, then introducing this Z is not required. Okay. So this is how we write the forward propagation. And now the important part is we'll go to write the backward propagation. I'm pretty sure most of the students don't get this, so I request you guys to be quite vigilant when I do the back propagation. or if you know it, that's really great. Backpropagation. So let's so basically here, right? Mm, okay. So first let's write for WW1 because that's easy to write, which is near to the output, and then we can write it to much more complex one, like probably for W21, probably for W21 or W22, any weight in the input to hidden layer. Okay. So can anyone tell me? Can anyone tell me what is the update rule equation using gradient descent backpropagation for WW1? So WW1 is equal to what I should write. You can look at this parameter update rule. Tutorial 1 was quite interactive. I don't know. I like tutorial 1. Okay, so basically, the WW1 minus eta dou FE divided by dou WW1, right? So this is what we need to write. And in this case, we need to find the equation. We need to find the value for dou FE by dou W1. So that basically means we need to take what's the change of an error function or a cost function with respect to this particular parameter, right? So dou FE divided by dou WW1. So this we need to write. So we just have to use a chain rule to get the value for dou FE with respect to dou WW1. So how do we write this? So here, FE is a cost function, right? We just have to work the backwards because the name tells us the backpropagation. So what actually happens in this case is we use some data, we use some random weight values, and we introduce some nonlinearity. And with all this, when it propagated forward, we come up with some value, right? But we have something else already for supervised learning, right? So that's called the truth value. So the main goal is to tune all these parameters, weight values, bias values, everything, all these parameters in such a way that the difference or the error between the predicted value or the output value with the truth value should be very less. It should be minimum. So we should minimize the cost function, right? So that's the idea. So what do? We take we take some kind of loss function to measure what's the offset of the actual value with the truth value. I mean, the output with the actual truth value, and we just propagate that offset back so that we can tune the weight values to minimize the cost or the error, right? So you get the point why we need why we are introducing the backpropagation algorithm, right? So now I just want to go the backwards, right? So it's dou FE with respect to dou C. This is the first output, and then from dou Z, I just have to go backwards, and the immediate next point I reach is the Y3, right? So dou Y3. And then from dou Y3, the immediate next point that I reach is net3, right? So it's dou Y3 divided by dou net3, right? And once I reach the dou net3, if I take, so the immediate next parameter itself is WW1. So dou net3 divided by dou WW1. So this is the chain rule. This is how we write the chain rule. Any doubt in this particular equation? Like, or anything else? There's something which you didn't understand. Sorry. is Z not equal to Y3? Yeah, Z is equal to Y3. That's what we have written here. Z is basically equal to Y3. So that's what I told. So if you have not introduced this Z, then it probably would be directly dou V by dou 3. Right? I'm sorry, my throat. So since we have introduced that, we just took the Z. But by now you probably understood that this value will goes to 1 because Z and Y3 both are same, right? So that value will goes to 1. Sorry. Yeah, right. So let's erase this. Okay, so now let's write, sorry. Now let's write what is dou FV with respect to dou Z. So just look at the cost function. That's dou FV, right? So sorry, FV is T minus Z whole square. So if we differentiate this with respect to Z, that's basically is minus 2 T minus Z, right? Is it clear? Because this is quite an important thing. See, if I just change this error function to something else, you just need to be very careful with the differentiation. And I'm pretty sure in the final exam, if they give any other cost function, they should give the differentiation as well. That I assume. Okay, so this is this clear? So that's the idea. Basically, you need to take a differentiation with respect to the output. Differentiation of the error function or the cost function with respect to the output. Minus 2. So T minus Z whole square, right? So yeah, the question that you asked is basically the question from the high school. So say T minus Z differentiation with respect to dou Z, sorry, dou Z, okay. So what happens is this is the power, right? So this 2 power of T minus Z, right? And then T is T minus Z. In this, we still have to differentiate this, right? So that's basically is minus 1, right? So minus 2 T minus Z, right? So did you understand? Yeah, even my problem, don't get confused. Because if anyone looks, this also looks Z and Z. So but I'm really sorry about that. It's a square. It's a square error. Okay. Okay, so now we just did the and so if you draw the diagram, you can just follow it. What is that? Is it for me or is it for the other student? Or you would want to say if you draw the diagram, then it's easy to write the backpropagation. Yeah, I think the student will come back. So we have written the differentiation of cost function with respect to, just asking if it is always the case. I'm sorry, I really didn't understand your question. See, my point is if you write the diagram, if it's possible to write a diagram, because in this case, it's pretty easy to write the diagram, okay? I'm pretty sure, I think in this course, we have 2 to 1 is what the max. So in that case, you can always write the diagram. And if you write the diagram, it's pretty easy. And even after writing the back propagation for WW1, and I'll show how to write directly, even without writing all this chain rule. We just look at the diagram and we just can write the equation, right? So that's pretty easy. I'll show that. We'll come back to that, okay? I'm pretty motivated right now because I see some interaction, and that's great. Yeah, I was pretty feeling low when I started the tutorial. So, so this is the first term, dou Fe divided by dou Z. We just wrote the cost function's derivative with respect to Z. And then the second term is dou Z with respect to dou Y3. So if we go here, dou Z with respect to Y3, it's basically is the same thing, and the differentiation is 1, right? Right? So next term, next term is dou Y3 with respect to dou net3, right? So we just have to go here. So we see the equation here, dou Y3. So here it's Y3, and then what's the dou Y3 with respect to dou net3. So here we have only the activation function. So that basically indicates that we need to take the derivative of the activation function. So here there is some concept that you need to be very clear of because it is very essential. So here I'm taking the all pass function. So in this case, can anyone tell what's the differentiation of the all pass function? So here I don't get confused since I'm introduced X here, but it's basically is this. So with this, I think you should be able to tell me what's the differentiation of Y3 with respect to net3 for all pass activation function. Or I can reframe the question in this form. What's the differentiation of net3 with respect to net3? Correct, but what's the value? That's correct. What you told is correct, f dash of net3. But in this case, what's the value, final value? What is this equal to? Yeah, it's 1, right? Because the slope is always 1, right? Because this is an all pass activation function, right? So that's correct. So dou Y3 with respect to dou net3 is nothing but 1 in this case. But here's where the catch is. So for example, if I've taken for example, one second. If I've taken the ReLU, so ReLU is basically is f of x is equal to max of 0 comma x, right? So in this case, if instead of all pass function, if I've taken the ReLU function, then what would be the differentiation? You can look up to internet or anything, or here it's pretty easy. So here it's max of 0, right? Max of 0 comma x, right? So that's what the ReLU is. So if it's 0, the slope is 0. If it's x, it's always 1, right? So this is how the ReLU looks like. So for any values less than 0, the slope is 0, right? Okay. Yeah, I think so you guys didn't go through all this in the lecture? So just want to make it a bit more complex. So if I want to use this all pass function as a sigmoid function, okay. So now, so if I call y3, dou y3 with respect to net3, where the activation function is a sigmoid, then what would be the differentiation? This is pretty tough to tell, but I'll give you the answer. So that basically is f of net3 1 minus f of net3, right? So if you solve it, so if we have used the activate sigma activation function here, instead of 1, what would we be writing? We would be writing f of net3 1 minus f of net3. This is what I wanted to convey. You're getting the point, right? What I'm trying to tell you. Understood? Yeah. Yeah. So this is pretty important. And even if you see, I just want to tell you guys, introduce one more concept here. See, for example, if see, we have different activation functions, right? So based on the task, we can use particular activation function. It basically make our neural network more efficient, right? So for example, if I use all pass activation function, it doesn't do any nonlinearity, right? It's as good as the linear regression or a linear classification, right? Which we did in the lab 2, I guess, linear discriminant function, right? So there's nothing being contributed by an activation function. But if I use ReLU, it's pretty easy. There's nothing much when it comes to the complexity, right? It's pretty easy. Whatever there is something to learn that's above the positive value, it just leaves everything. It doesn't bother. Is there any curve or anything? It doesn't bother. And the differentiation is only 1. It's pretty easy when I use it for the backpropagation algorithm. But it's not the same thing with the sigmoid. When I use this sigmoid, so this basically will go like this, right? Like this, right? So as it goes to the higher values, the learning is too small, right? The learning is too small, right? Is it getting complex, or is it you guys are understanding it? So my point is basically, if we use sigmoid as we go for the higher values, the learning is too slow. We might not learn at all, or we might be just stuck with a slower learning rate, right? And one more thing is, with this we can hit up this exploring or delimiting learning as well, right? And look at the differentiation. Differentiation is too big, too much to calculate. So if we use this in the backpropagation, it just adds up some more complexity, right? So saying that, we can't just ignore the sigma at every point of time. We can use it in certain tasks where it is actually required. And our tasks of learning is mainly restricted in the few standard deviations of uh, learning curve of sigma, right? So that's one concept that I wanted to introduce. So these are very helpful when it comes to practical implementation of neural network in your problems. Okay, what kind of activation function I need to choose? Okay, so now just to not confuse you, just tell me what is dou y3 with respect to net3 in this particular problem. Yeah, so you guys are intact. So you guys are not lost. That's great. Okay, so now we have the last term, that's dou net3 with respect to dou w1. So for that, we go to net3. Net3 is here. So we need to take the differentiation with respect to w1. So if someone is not clear, let me write it properly. Okay. So dou net 3 with respect to dou WW1. So that's here. So here we need to, if we see the dou with respect to WW1, so this whole thing will be a constant and it just goes to 0, right? If I differentiate net 3 with respect to dou WW1, then the answer is only W1, sorry, Y1, right? Yeah. Yeah, so that's correct. It says just Y1, right? So the final answer is -2 T minus Z Y1, right? So this is just nothing but dou FE divided by dou WW1. So now let's get back to WW1 update rule. So that's WW1 new. So we take WW1 old minus, or I can say plus, eta 2 T minus C Y1, right? Just give yourself some time and just look at the equation and the diagram and try to develop some intuition. And I'll explain how to write the chain rule even without writing these equations. So it will help you to develop some intuition so that you can directly answer, because this final exam is a multiple choice questions, right? So you don't have to spend too much time writing these calculations, but you should be able to write the final equation. So. All good? Like 4 and what? I really don't know because I'm not following the lectures. But as far as I know, if the same format has been adopted from the last semester, then it should contain the questions from all the lectures. So it's basically cumulative, right? It's not just topics after the midterm. It includes everything. But please verify with Dr. Lay. And I have not set any question for the final exam, so okay. So till here, it's all good, right? Okay, so then that must be correct. So you probably get more question from 4 and 5 lectures, and then a few questions. Yeah. So basically, some questions, it's very tough to quantify some, right? So what's best is understand and study everything. That's what is the best, right? So, but going forward, if you want to claim yourself related to data science or artificial intelligence, you basically know more about the neural networks and the unsupervised learning compared to machine learning algorithms like Bayes' theorem. Having said that, it doesn't mean that you should neglect those, but give more weightage to neural networks and unsupervised learning, because topics will build on top of those. So anyway, so coming back to, so this is clear how to write it. We just wrote for WW1, right? We just wrote for this path, Okay, so now let's write for W21. Okay. So this basically take the path starting from here. So can it go through WW2? Yeah. So it should go through WW1, right? It should go WW1. And should it go to B1? So if you want to think it should go to B1, let's go to this equation. So for W21 to affect, it doesn't include anything with the B1, right? But for net1 to affect, B1 is required, right? So it's not required to go to B1 and come back to go to W1. You know what I mean? It can directly come to net1. But for net1, B1 is required. You know what I mean? There is some catch. You just need to understand that. Give yourself some time and try to understand. You got it? Got it? Or you still have some question on that? Yeah, so you got it. That's good. So this is the path, right? So now we want to write it for W21. So what is the equation? Backpropagation update rule. You can unmute if you want to talk. I'm not sure you guys can unmute. Okay. Yeah, so you wrote just W1, but it's W21. I can understand because it takes time to type. So, but you're correct. W21 minus eta dou FV dou W21, right? So this you don't have to even get confused to write it. You just have to write it because there's nothing else to go wrong in this, but writing the update rule, right? So it's just parameter new gives with the parameter old minus eta dou FV with respect to dou parameter. By the way, why we have introduced this eta? Yeah, that's learning rate. But if you remember, initially I told you a concept, right? So we basically have some random weights and the data, and when we do the forward propagation, we come up with a z. That's the output that's calculated based on the random weight selected initially, right? But we have something called truth values. So what is the offset between the truth value and the calculated output? We just need to minimize that, right? So to minimize that, we use the cost function to decide how the offset has been calculated, and then we back propagate that offset to tune this tune this parameters, right? And what scale we need to do the tuning. Should we do it in the bulk? I mean, not bulk. Should we do it in the larger scale, or should we do it in the smaller scale? So that's what this eta tells us to do. So if we take the bigger value of eta, we just do the too much of tuning basically, and it probably might uh, pose another problem of overshooting. So for example, this is our error curve, the FV, and we are trying to, so initial error is somewhere here, and then we take the dou FV with respect to parameter, and it probably might come here. And this length, how far we should go, how far is it, should be very long or should be very short, that is what decided by eta. You're getting it, right? So if you take very large eta, so instead of jumping here, it might jump here. right? So then there might be a faster learning, but there is some other issue. So we are supposed, this is the minimum error, right? So we are supposed to come here and stop the learning. But if we take very large, this might again go here somewhere here. It might overshoot. And then obviously it won't go in this direction because they're using negative value. It should go in the forward downward direction, and then it might shoot again here. It might shoot again, shoot. So it takes a longer time. So if you take it very smaller value, so instead of jumping here, it might jump here, the error value in the next iteration. So it might do very small jumpings. So this will take forever to come to this minimum point, right? You're understanding what I'm telling? So if we keep the smaller value of eta, it might take a longer time to learn. If it's longer, then there is a problem of overshooting, but there is an advantage of faster learning. So there should be some way to decide that, right? So that's why we have to do something called adaptive learning. So say if our error value is too far from the global minima, then take a longer, bigger eta value, then take a longer steps. As it is approaching towards the minima, then reduce this eta value so that we just don't overshoot. This is what is done using Adam optimizer. So if you have seen the TensorFlow or PyTorch or even in the MATLAB, so you just have to introduce the optimizer, which does this adaptive learning rate. Oh, by the way, this Adam is introduced by UOT people. Okay. So you guys understood why this eta is introduced? There might be one mark question or something like that around these. But is it understanding or is it boring? Or you guys are catching up? Okay, it's understood. That's good. I'm pretty sure it's not redundant, right? So this information is not redundant, right? It's like basically what I mean is you guys knew it already, or is it like, if you knew it, let me know, because I just don't want to waste the time. Okay, that's good. So now let's come back and write the equation for W21, okay? So W21 is, so here, if you see this particular equation, just to develop the intuition, see what we did is basically we took the differentiation of the cost function with respect to the output, right? And obviously we need to do that here as well, right? Because we just need to do the differentiation. We just need to take the chain rule to find this dou FV with respect to dou W2 in this path, right? So dou FV divided by dou W21. So I'll just write it. Let me see if you guys understood or not. Minus 2 multiplied by T minus Z. Is it correct? And this is necessary to write, correct? Yeah. So now we have done doing the differentiation at this point. So from the output, the next point we are reaching where something can change the output is Y3, right? So, but we know that Z is nothing but Y3. So is there anything to change the output? So there's nothing. So differentiation should be 1. So then we go from this Y3. Now we are at this point. We did the differentiation at this point, and then we saw there's nothing to change in this path because Y3 is nothing but Z. And then from Y3, we need to go to net 3. We are pretty sure there is something to change the net 3 when it goes to Y3. What is that? What changes the values of net 3 exactly? So activation function, right? So activation function, we cannot ignore that. So here, what is the active differentiation of the activation function? One, right? So we have to write that. So let's write the differentiation of the activation function. So now, so obviously we cannot go in this path because we know that there's not, I mean, for W21, there is nothing to do with this path that changes the output, right? So now we are done till the net3. So now from net3, we can go to Y1. So is there anything in between the path that can affect the net3 from Y1? So see here, there was nothing, and we didn't do, there was nothing here in between to change the value for Z contributing from Y3. But here, value for net3 has been changed upon some value based on Y1. So this WW1 is changing the value of Y1 to contribute towards the net3, right? Yes or no? Yes, because we know that, right? So net3, we write it WW1 Y1 with plus we write something along this path as well. But we know that WW1 is changing in with respect to, I mean, in the combination of Y1 to change the net3, right? So we can't ignore that. We have to take that into consideration, and let's write WW1. Okay. So this might look crazy, but you will be amused once you know how we are writing it. So from Y1, we have to go to net1. So is there anything in between net1 and Y1 that can change the value of net1 to contribute towards the Y1? Yeah. So again, the activation function differentiation is 1, right? So we will write 1. And then we are at the fag end of the path. So here we need to take a differentiation with respect to W21. But is there anything else that can change the value of net1 with respect to, with the combination of W21? X2, but W21 we don't have to because we are taking the differentiation with respect to 1, right? So that's the parameter that we, exactly. So it's just X2, right? So the final equation is T minus C WW1 X2. So now let's cross verify. So now let's cross verify by writing a chain rule. So dou FV with respect to dou Z with respect to dou Y3, dou Y3 with respect to dou net3. What is dou, what should I write next? Dou net3 with respect to? Well, yes, correct, dou Y1. So then dou Y1 with respect to? What is there in the path? So in this, no, just look at it. Yeah, net1, right? Not the, some student told, one of the students, he just told W21. I just want to focus on that student. Can you just tell me why did you tell Y21, sorry, W21? Because I think you looks like you didn't understand the concept. So let's go here. So from Y3, we are going to net3, right? So we're not skipping to go to WW1, right? So similarly, when Y1, we have to go to the next step, and next step is the net1, right? Okay, yeah. I understand. Yeah, that's why I used a different notation. So my point is, if we don't stick on to the notation, but if we stick on to the concept, then we should not be in any problem. You know what I mean? Because if you read the different research papers, um, artificial intelligence is pretty crazy, because in this field we don't have only mathematicians to work on, or is it like we don't have only the engineers working on? Because if we have one community, then it's pretty easy that they use the similar kind of notations. But since this artificial intelligence is with a wide diverse fraternity, people use all kinds of notations, but end of the day, if you know the concept, we should not be in a bad position to understand it. So my point is, if you read any research papers, but if you know the concepts, it should be able to easy for you to pick up the things rather than adhere to the concept with the notation. Okay, so donut one, and then from donut one, where should we go? You can look at the forward propagation equation, or else you can look at the diagram. From donut one, where should we stop? Exactly, because we are taking the derivative with respect to dou w to one, right? So now, so we know that dou fe with respect to dou z is basically minus 2t minus c, right? And dou z with respect to y3 is basically 1. And y3 with respect to net 3, if we take it, the derivative is 1. And dou net 3 with respect to y1, if we take it, it's ww1, right? Understanding? And dou y1 with respect to net 1. So y1, it goes to here. Y1 with respect to net 1 is 1. And then dou net 1 with respect to w21 is x2. Understood? So any doubts in this? So finally, the equation is w21 is basically w21 plus 2t minus z ww1 x2, right? Understood? So now the last thing that I want you guys to do is for B2. So without writing the chain rule, can anyone tell me the equation for B2? B2 in the sense, I just want you to tell me the dou FV with respect to dou B2. Or you can solve it and let me know later, or send me an email if you have any doubts, okay? So that's related to the backpropagation algorithm. So this is pretty simple, neural network that I took, right? So now just to make it a bit more complex, let me use the other, the bit more bigger neural network, so that you will know how to write. For example, if multiple branches involved, so a student wrote it for B2. Well, you're 100% correct. Oh, you sent me in a direct message. You could have posted that in the to everyone. You're right. That's correct. So I'm pretty happy that students have picked up the concepts how to write the backpropagation algorithm. That's good. That's good. I appreciate. If you don't mind, is it okay for you to post that into everyone so that the other students can also just look at it? Yeah. So any other students, any issue, any doubt with that equation for the B2? The student has written it, the final value, but I just asked for dou FE with respect to dou B, but oh no, it's dou FE with respect to dou B2. Yeah. So any doubts with respect to dou FE with respect to dou B2? And just give yourself some time, look at the forward propagation equation and the diagram, and just cross verify with the equation. So what the student has done is basically, so the student has taken the dou FV with respect to dou Z, and then from dou Z, student has went to dou Y3. So from dou Y3, took the dou net 3 with respect to go to B2 should be should take with respect to Y1 or Y2. It's Y2, right? So dou net 3, dou Y2, and then dou Y2, then took dou B2, right? I think I missed the dou net 2 as well, right? Dou net 3, dou Y2. Yeah, dou Y2, dou net 2, and then dou net 2, dou B2. Yeah. Is this correct? Yeah, so look at it. So Y2 should not be there, right? It is just WW2, right? Yeah, you're correct, Vincent. So cross verify with this equation. It's 1, right? Yeah, it's 1. But what I appreciate, at least in that speed, the student tried to write it right. So obviously that's fine. Even if issues are there, that's fine. But you got the idea, right? So the first point you should keep in mind is so this semester I'm not getting much time to interact with the students regarding the labs. But the previous semesters when I talk to students, they're pretty they feel pretty daunting when it comes to backpropagation. They don't understand it. So don't think that backpropagation is tough. It's pretty easy, right? As far as you know the concept, it should be easy. Okay, so now let's go to the last problem so that we don't take much time. So after this tutorial doesn't take much time. Tutorial is It's just solving those problems based on these concepts, right? And I don't take much time for the unsupervised learning because that's pretty easy, right? So in this case, let's assume we have x1. So I want to take x3 and we have xn number of inputs. It's a multi-dimensional input, okay? And then in the first hidden layer, I'm changing the notation again. So I just want to know that how you guys have understood, okay? F3, F4, and Fy. And in the output layer, I just want to keep it F6, okay? So this is the input. Okay, so this I want to call this as W31, W32, and this I want to call it as WW11. Okay, so in this I want to use the error function t minus z whole square, but I want to use the activation function sigmoid. So that's 1 plus e to the power of minus 6. So the differentiation of sigmoid, as I told earlier, it's f of x multiplied by 1 minus f of x. Okay, this is the differentiation. And I want you guys to write the dou fe with respect to dou w32. So for this, so the path, so from F6, which one I should take to go to W32? So obviously I should go to the F3. From here, I can go here, and this is one path, right? And the second path is this one, right? And the third path is this one, right? And obviously I don't have to go to, from F3, I don't have to go to this, go through this path. Similarly, from F3, I don't have to go this path. This path, and from Fy, I don't have to go this path, right? So now, I start to write the equations. Let me know if you follow or if you get any doubt. This is correct, right? And then we have F6. So here, if you see, I've not introduced the Y6, right? So that's redundant. So I didn't introduce that. So I just took the Z as the direct output, right? So here, that's 6. So since all three parts join here, I want to take this as a common. So I just want to common this out, because this will be there if I write to the individual parts. This will be there in all the three paths, right? So I just want to take this as a common and put the big bracket. And now I want to write in this first path. Let me know if you don't follow or if you find any problem. I'm pretty sure most probably all the students will understand. So from here, where do we go? WW21, right? So again, all these paths will join at F2. I can take the common out this part, right? So I don't want to write that part. So I just want to move to the next path. That's WWW2 F of net 4 1 minus F of net 4 and then WW22. So this path is done, and now I'll write the last path. So that WW3 F of net phi 1 minus F of net phi, and then we have WW23. So now all these path converges at F2. So then I finish this, I end this big bracket. So I can write from F2, right? But is it clear? Is it any doubt why I'm doing like that? So F net 2, 1 minus F of net 2. And then finally, we are taking the differentiation with respect to W32. That's why the final one is X3. So this is just dou Fe with respect to dou W32. But if I write it to the update rule, that's basically is W32 plus 2 eta. I don't want to write 2 eta. And then all this stuff, everything comes here. So is it clear or any doubt with this? Oh, that's great. Pretty easy, right? Now, what do you feel back propagation? Is it tough or is it okay, or is it easy to approach? Yeah, right. So similar, same thing with any tough concepts, basically. Yeah, yeah. My point is that basically, if students develop the intuition, there's nothing like that, because anything that falls into your subconscious memory, you don't have to worry too much, right? So that's where the students score low. Students basically try to by heart, but if they develop the intuition, what's to write and how to write, then it's easy. So now so this is the maximum possible or biggest possible neural network we can ask you in the final exam, right? So if we give this, it's pretty easy. You don't take much time to write this very big equation, right? So since it's a multiple choice, it's very easy that you can write it like in a moment, right? So now I think we have spent good amount of time regarding the neural network. Then I think we can jump to practice problem. So let me just, so I suggest you guys to pull up your that document, that no. So since it's a multiple choice, you don't have to draw that diagram, but if it helps you to answer, obviously, yes. But make sure that what kind of notations used in the question, because here, if you see, I've used different notation in this problem and different notation in this. So make sure that what kind of notations used in the question, and you don't have to draw the graphs because it's a multiple choice question, so fill the blanks. But if it helps you, draw it out on your working sheet, and then if it helps you, that's great. See, for me, I personally would draw the neural network because it's easy to follow through, right? You know what I mean? Okay. So I suggest you guys to pull out your document because I don't have to write each and everything. I just read out. I'm already a bit stressed. So is it okay if we take like 5 minutes, 3 minutes, 4 minutes break, and then we come back at 7:25? So we can discuss on the tutorial problems. Okay, that's great. I'll just pause the recording. Yeah. Okay, so let's go to tutorial problems. So my expectation is right now with all the basics that we learned, based on this, I think it should be very easy for you guys to solve these practice problems right now. All right. So the first problem they say, so yeah, before starting, I suggest you guys to pull out your documents so that it's easy for you to follow, because I don't write it much on the tab. So the first question is, consider a standard 3-layer neural network. So basically they say 3-layer, which consists of input layer, hidden layer, and the output layer. So this is what they mean. 3-layer neural network trained using the cross entropy criterion function. So the error function in this case, they're going to cross entropy criterion function. So they changed the cost function. We were just considering the square error cost function, right? But in this case, they're taking the cross entropy cross function. So here TK is the truth value, right? ZK is the output from our neural network, right? So then when we say we need to take a differentiation of this with respect to the output layer, right? So, and then they're asking us to derive the learning rule, that's delta WKJ, or KJ, they basically represent this, right? So whatever the number of neurons, so this they call it as WKJ, right? So that's the hidden to output weights. And then they're asking us to derive the learning rule for WJI for the input to hidden weights. That's from here, right? So these weights. So there we initially took 2, 1 or 1 to right. So here we are just increasing the complexity, right? So that's WJI. So we need to derive the learning rule for WKJ and WJI, and they're giving some hint. What is that? Hint D of ln X, or they're just giving the derivation. So now I just want to let you guys to help me to write the chain rule for the WKJ. So when I say WKJ, can anyone tell me the final update rule? So here they're telling WKJ, that's the, it's not a, so here I just missed to tell that, right? So this part is delta parameter, right? So which is nothing but minus eta dou FV divided by dou parameter, right? So they're just asking us to get this. So we don't have to write the this part. So when they say WKJ, that basically is minus eta and dou JCE cost function with respect to what is the parameter? Yeah, because here is not just one parameter, it's the whole lot of weights in this hidden to output layer, right? So it's WKJ. right? So now we need to write dou JCE with respect to dou WKJ, right? So they say they use ZK, right? ZK as the output. So now can anyone tell me what is the first thing I just have to write? Dou JCE with respect to dou. Yeah. So here they use the K, that's why ZK, or else you're correct, dou Z, right? So that's the first thing. And then from dou ZK, where should I go? The next thing. So ZK should consist of activation function in this case. So net K, ZK. This is the output if I write it the, oh yeah, net K, right? So that's the activation function. So go back here. So what we did here, we took dou FE with respect to dou Z and then dou Z with respect to dou net 6, right? Here, net 6. So, but here instead of 6, it's basically is a K because we are taking all the neurons, right? Net K. Confusing? You're following up? Don't try to look at the solution and tell the answer because you don't understand. Basically, if you learn it today, you don't have to reread again for the exam, right? That's what my point is. I don't want any student to lose any marks when it comes to backpropagation. So is it clear or is it confusing? Let me know. So you're clear why we have written net K, right? Oh, it's pretty inactive. Okay. So then net K with respect to the last parameter, that's we are going to the weight values, that's dou WKJ, right? So dou JCE with respect to dou ZK, we just have to take the differentiation of that cross entropy function, right? So go through the math that's given in the solution, and they say the final answer is minus TK with respect to ZK. Sorry, minus TK divided by ZK. Okay. And then we need to take the activation functions derivative, right? But here they have not mentioned what kind of activation function we are supposed to use. So when we doesn't know, we just basically tell that we need to take a differentiation of activation function. That's what the I think it was Hamza who told that f dash of net in the initial. So since we don't know what happened to summation, which summation? Oh no, there are steps to exactly the solution is given, right? So this summation we just have to expand it, right? So to differentiate that with respect to the ZK, and then there are a few terms which goes to 0, and then we left with natural land TK natural land of TK divided by ZK, and 1 over x that basically cancel out the TK, right? So we get minus TK divided by ZK. So that simplification is given in the solution. Just go through that. I don't want to talk more on that. Um, uh, So we were something else or somewhere else where, okay. So that's the f dash of net k. And why does every other go to 0? Oh, that's the question from the high school again. See, t ln of how do you do the natural log ln of x1 by x2? That's ln x1 minus ln x2, right? If you expand that using the identity, and when it's t1 minus ln t1 minus ln t zc, that basically cancel out, right? It's plus minus plus minus. Yeah, so those simple things, I think you can spend time to that's fine. Even if you get those doubts, even if you get those doubts, you can send me an email as well. I'll try my best to help you guys. Okay, so f dash of net net k, right? And then the last um, uh, value is dou net k with respect to dou wkj, right? So here we need to write the forward propagation thing, because we have multiple weight values, right? We have to take the summation. So what happens is basically wkj multiplied with, so based on these guys' notation, so they've used yj as their value, okay? Plus wk0 as a bias. So if you take wkj, that basically, so oh yeah, that this simplifies. I think they've given this diagram that will simplify everything. So tk zk, and they've used y1 as the notation. And the bias, they call it as yn plus 1. And all this weight, they call it as wkj. So if you write the forward propagation, then net 6 is basically equal to, sorry, net k. Net k is basically equal to summation for j is equal to 1 to n plus 1, right? And then wk0. So if we take the derivative with respect to wkj, that's only the yj. And everything else goes to 0, because that's the, so that's wj, right? So is it clear? Is it problematic, or do you feel it's okay to understand, or any confusion? And then they're asked to write the notation for the weight values for the wji, right? So for that, dou jce with respect to dou wji. Dou jce dou yj. So any doubt in this? Just give me a second. I'll be back in like 1 or 2 minutes. I'll pause the recording and come back. Just let me know if you have any doubts in this. Yeah, sorry. So this is pretty clear, right? How to write it. And if you have any doubts, let me know over email. I think we can discuss. So for now, there's no any doubt, right? So we can go to the second problem. So second problem, they're telling us to consider a sigmoidal activation function So in the sigmoidal activation function, they're using the parameters A and B to scale. That's good. And then the first question show that its derivative is, yeah, it's pretty easy. So I don't want to spend too much time on that. But if you have any doubts, you can let me know in hours. So the second 2A, basically the question asking us to find the derivative f dash of net can be written simply in terms of f of net itself. So this question, initially I just told you guys that, I deleted that. So sigmoidal functions derivation, right? So that was, so f of x, I use 1 plus e power of minus x, right? So the differentiation of this, we showed that f of x with respect to 1 minus f of x. So this can be, see, I'm trying to go backwards. I just want to show one thing in this. See how bad it will be if we don't, is there a, I mean, is it possible to pull out from the internet? So differentiation. If there's a link that I can find, I'll show you that how ugly it looks if we don't write it in terms of the input. So here the point, the concept is we are trying to write the differentiation of an activation function in terms of the activation function's input itself, so that it's easy for us to save on the complexity, so that it's easy for us to write the backpropagation algorithm, right? Okay, I don't find the okay, I'm not able to find it in the internet basically. So why they've asked us, is it possible to write, or is it write the f dash of net in terms of f net, is basically for this. So for the backward propagation, it's easy for us to save on the complexity, right? So that's why they've asked us to write the f dash of net in terms of f of net, so that it's easy for us to save the time. So so if you have, okay, I think I can share the solution itself just to show it. Oh, where is the solution? Dash of net. Yeah. So let me share the screen. Oh, I need to stop sharing this. So if you see this, you can see the, yeah, you can see this. So f of net is basically this equation, right? So this equation, right? So this equation, when we take the differentiation of this big parameter, is it possible to represent the differentiation of this with respect to the f of net itself? So f dash of net, we do all sorts of solvation. Obviously, we don't ask you to do it in the final exam, because yeah, even it's not possible to frame a question saying that what is the missing step in this particular differentiation. We cannot form the question, so you can't expect any question from the second question, but it's an important one as well. Not in terms of the exam point of view, but in terms of the future, right? If you want to understand the intuitions. So they do all sorts of calculation, and then finally comes to the point And they express this f dash of net as b by a multiplied by a square minus f of net square, right? You see this how beautifully it looks. But if you stop, it basically stops at this point, right? This point. How bad it is, this particular equation to calculate, right? In the back propagation. You know what I mean? There is this e and there is this exponential and there is this division, all sorts of stuff, which is pretty complex when it comes to the implementation, right? So they do all sorts of gimmicks to come to this particular point where we avoid the division at least. And even the exponential form, we just have a square. It's just multiply the same element twice, that's all, right? And subtraction is very easy. Obviously, this we cannot avoid it. So usually in the conventional activation functions, they avoid all case of coefficients. So this is the special one. I think this material is framed in 2004 or 2003 or something like that. It's pretty old material. So these days they avoid all these kind of coefficients. And even if you take a double differentiation, we just represent it as f net multiplied by first differential equation, that's f dash of net multiplied by minus 2b by a, right? So you know why we write in this format, right? So that's what my point is. And then we discussed about the shooting and the delimiting ability of the activation function. If we use sigma for the larger values, the learning is very slow. That's what we discussed earlier, right? So that's the second question. So what's the value of f net and f dash net and f double dash net? So basically activation function, the differentiation and the double differentiation of the activation function when minus infinity, 0 and plus infinity, right? So you can see f net at the minus infinity, it's basically minus a. So that's the scale between minus a and plus a, right? So though our equation is this, b is not even contributing to anything, but a is trying to limiting the activation function, right? So this, in case of differentiation, it's AB at the 0, but for the higher values, it's almost 0. So this basically introduced this vanishing gradient problem, right? So this is not a good activation function to consider. You're understanding? And if you take a double differentiation, everything goes to 0. Basically, there's nothing to learn, right? So that's the intuition behind selecting the different activation functions. And the second problem is talking about that, okay? And then the third question is very interesting question. So briefly discuss the following with respect to multi-layer neural networks. Use figures as appropriate in your explanation if required, okay? The first question is the importance of using a validation set in training. So let me share the screen. So here, oh, have I started the recording or is it? Okay, it's recording. So here, say assume I have this, so this is a problem from some domain, okay? And I have this a number of data, and I'm using some neural network, multi-layer neural network, and I used all the data and I fed it to the neural network, and I got a model, okay? I got a model, and so this basically gives us some model, right? So probably x squared, x, or whatever. This basically gives some kind of model, okay? And this I go and and I deploy it, and I expect the new data to come. So what would be how would you expect the output? Say this domain, I think, to make it much more interesting, I would say this problem belongs to, so in the data, we have different features that tells whether I need to hire an employee or not. Okay. And I have a data, hired n number of people, or even rejecting the employees, and then I made a neural network to decide. So basically, the HR itself can take the data based on the resume and just wants to give this new resume into this model, and she wants to know whether to hire or not. Okay, so this is the problem. So what do you expect? So I just use this n number of data and I come up with a model, and now I'm trying to make a decision based on the new value. What would you expect? Would it work better or not? Obviously, the probability going wrong is only 50%, but and I want to add wait list as well, waiting list. Now I'm reducing, even I can add much more to reduce the probability of going wrong. What would you expect? Now, can you just let me know if I've done any mistake in modeling? Any thoughts? Yeah, the question basically, so HR, so HR was taking different features, okay? Different features, X1, X2, X, and features. So based on these features, HR was taking the output as well once after the interview process to hire or not to hire or put it in the waiting list, okay? So this, we have n number of data. This whole, we have n number of data, that's all. So I've taken this n number of data here, and I used a neural network, multi-layer neural network, to optimize and everything just to get the model, okay? And then I got this model based on this data, and then I deployed it, and the a candidate sent a new resume, and the HR was taking the data for all these features, and she don't know the HR doesn't know the output, right? Because it's a new decision that we're gonna make, but instead of a interviewing panel, but this neural network is helping us to make a decision. So the HR fed the new data to f of x. What would you expect the output? Will it be accurate or going wrong or anything? Or how would you expect this particular model to work? Have I done any mistake in this pipelining? Yeah. Yeah, we don't know. It might be correct or it might not be correct. We never know. It depends on the nature of the data. If the data is homogeneous, like whatever the first row of data is nothing much different with the second row of data for all the hired cases, and there's nothing much difference when it comes to the cases for all the not hired cases. If its data is homogeneous, then we might expect this new model would give us the accurate outcome. But if it's not, then we never know. The output might be something else, right? So when we derive any modeling, we just have to split it, right? So if I have a n number of data, I should use few of the data for the training. So obviously, when I say n, it's not a linear data, it's a shuffled data. We should not use a linear data because even the linear, I mean, I cannot just say linearity because there's no free lunch when it comes to neural network. So it definitely depends on the domain. So if a domain takes a continuous property of a data, then we don't have to shuffle it. But if it's not required, then obviously we have to shuffle it just to make it much more robust, right? So, but here assume that the shuffling is done because in this case, there is nothing related to a linearity or continuity, right? So we can shuffle in this particular hiring process example. So I've shuffled it and I've used the portion of it for the training and few portion for the validation. And then the rest I've used it for the testing. And then based on the testing, I can go for the deployment, right? So training, what happens is, so usually these days so it depends. For example, for some kind of, for example, anything related to satellite or astronomy based problem, it's very tough to get the data, so much of data. So what they do is, if they have a small amount of data, then they use 80% of data for the training and 10% for validation and 10% for testing. Okay. It depends on the kind of nature. So, but if you have large number of data available, then the good point to get started is 50% of training and then 10% validation and 40% to test. This gives much more confidence, right? Because we have tested on almost like a 3/4 of the data, and that gives us better confidence, right? So during the training, whatever the data we use, we don't want the testing data to be exposed. This is like we should forget it. We should forget it. So every epoch, once the training is happening, we use the validation set to check whether the training is going in the correct direction or not. Sometimes if you see validation accuracy is so high and the training accuracy is so low, or even the other case where training accuracy is so high, but the validation accuracy is so low, right? Understanding? So once that's done, so we see the validation accuracy is at some point of confident value, then we take this testing data set and then we introduce that to the model and we see what's the testing accuracy. If the testing accuracy is considerable, then we go for the deployment, and then we have this confidence that the outcome is always 70% confident or something like that. But since we don't know, we couldn't say how confident we are when it comes to the outcome, right? That's why even the student told it might be inaccurate or it might be accurate. We never know, right? So coming back to the question, you know the importance of using the validation set right now. Yeah. And then the second question is appropriate weight initialization in MNF. Exactly. So see, 10 years back, there was some kind of rule of thumb. People were using that Xavier approximation, but there's no free lunch. Right now, there's nothing called appropriate weight initialization, but it's always a trial and error these days because there's no free lunch. We never know. So, but previously this Xavier's approximation, what it was telling is we use this, right? So if you want to for the weights between the hidden layer and the output layer, we can use whatever the number of hidden layers. We can use that -1 over root number of hidden layers. So this is the weight, and then output I'll just use the WKJ. And this is what the based on the number of hidden layers. But there's no guarantee that this will always work, right? So, And for the weights for the input, it's the dimension of the input. That's 1 over dimension. If it has n 3 number of features, that's 1 over root 3. It's like that, right? Minus and then wkj. So usually these days, what they do is they take the they don't choose along the values of 0, just because if, can anyone tell me if I choose W30 as 0, what happens in this case? Can anyone tell me? Or if it's very, very near to 0, if this weight value W32, can anyone tell me what happens? Even you can look at the equation as well. Yeah, right. It's basically it's turn off. It's basically this whole part is turn off, right? It doesn't help us to learn, right? So the derivative is always 0. There's nothing learning in this aspect, right? So it's very safe that it's always between, to choose between 1, 2, or anything, any values quite deviated from 0, right? So if it's near to 0, it doesn't mean that it will never converge, but it will take a longer time to converge. So that's related to, what's the third question? Using a momentum term in backpropagation. Oh, this is pretty helpful. So momentum, right? So here, I think we use that. Oh, I deleted that. Oh, okay. Okay, so my bad. I deleted the. So I use this error function, right? So assume our error function error is here, and we are trying to uh, jump based on the eta values, right? So if the global minimum here is, our aim is to come here and stop the learning, right? But this is a very um, what do you call this? This is very ideal case, but usually error functions have, you will be very crazy, and this is too much of craziness. So let's take something like this. So if it's like this, so we come to this point where the plateau is so almost, there's a question. What's the final answer for B? What do you mean by B? Or question B? Oh yeah. So with respect to this particular course, you can tell that Xavier's approximation. That's that's what I mentioned somewhere here. This one. But when it comes to the practical implementation, yes, there's no good answer. So we just have to try based on your problem. See, for example, if you take image problem, the value is always between 0 and 255, right? Pixel values. So there the initial values is something else, right? And if you take any problem, like for example, this problem where we consider the hiring an employee. So in this, it depends on what kind of problem. If everything is categorical, then our value can be very flexible. But if it's everything is continuous values, and the values is all between 3 and 4, then it doesn't make sense to take the weight values between 0 and 1, because it will take much more time to converge, right? So then it's easy for us to take the weight values between these 3 and 4, or anything near to 3 or anything near to 4, right? So yeah, practically no, there's no correct answer. but for this course, you can use that. Even that's the answer given in the solution as well. Okay. Yeah. When it comes to the final exam, just stick to whatever the answers given there. Don't get confused too much, right? So going back to momentum. So in this case, right? So here there's no issue. So here things goes correctly based on the eta value, but here when it comes, the learning is very slow because the gradient values will be almost same, right? So usually the gradient, if it's going lesser and lesser, we know that there's some learning is going on. But when it comes to this plateau, uh, there's nothing much learning, right? But still we are not sure whether we are at the global minimum or not, right? Correct, Alan? No. Right? So then what do we do? Then we don't have to take all the steps. So then what we take is take the agglomerative of all the slope, because we are pretty sure that it's not going to be different in the case, and add it to the back propagation, so that we just jump to different value at a bigger leap. So for that, we add the momentum values, right, with the back propagation. We just add the summation of all the slopes for the back propagation, so that we make a bigger jump. I just want to see if there is in the internet, if there is a good example for that, so that you'll understand. Yeah, so there is this. Let me share. So this just keep this in the mind. Okay, I just want to stop sharing this image, and I want to share the other one. Okay, so just keep this in the mind. So this especially this particular plateau, and we just want to add the momentum part for the back propagation stuff. Okay. Don't worry, I don't take much time for the unsupervised learning, because that's pretty easy. Okay. Or what did I share? Sorry. Okay. So here, if you see the back propagation, so they're taking this learning rate and weight gradient. So if it doesn't add any momentum, it will take the smaller steps. But just to add the momentum, we add this the summation of the gradients of previous all the gradients. Okay, that's with the momentum factor. Usually this momentum factor, we can keep it to 0 or 1. If it's 0, then we basically remove this momentum stuff, right? But if it is 1, then we just add all the previous gradients, this W till the point t minus 1. We take all the, so that we make a big leap, and then we just go over the momentums, plateaus, just to avoid slow learning. You know what I mean? So you got it? So we add this momentum. So have they used any diagram? Okay, they have not used the diagram, but I've used the diagram, so you got it, right? So if you don't use the momentum, this is what the back propagation upgradation rule, right? So, but if we add the momentum, we add with the momentum factor and the gradients of all the previous stuff, right? That's clear? It's clear why we use the momentum? Yes, yes, that's great. Okay, so the last question, 3 options for improving robustness when training set is small. Oh, this is very practical question, because this is the question, this is the problem we arrive every time when we go for modeling. See, the question is, this N, we have very small amount of data, right? So what all things we can do to make our model is quite robust? Can you guys think of? You need to be pretty creative and crazy when it comes to modeling a robust model, basically. So is it possible to add some noise to the data? Noise with respect to the data. And we add the noise in the modeling as well, so that we don't just model the data, we add the noise with the data as well. So will that work? Yeah. And the next thing is when it comes to deep learning, we do something called augmentation. You know what's augmentation? So we have one image that's with a blue background, and there's a parrot or something like that. So instead of blue background, we create multiple images with a green background, but same parrot. It's green background or red background, different. So with this, we're just augmenting the data. So will this work? That works, right? So we can add we can do the augmentation. Basically, we can create a new data using the older data, right? Yeah. So that's it regarding the neural network. So if you have any doubts, let me know. Is it useful? This session is this useful, or is it boring? Anything that I can improve? Don't we need to think of 3? Oh, based on the domain, you can do n number of things. Okay. See, for example, there's something called component analysis, right? So you can do the eigenvectorization of your data and add that as a new feature, right? So we can do multiple things based on the domain, what kind of problem you're trying to do, right? I didn't understand what is think of 3. Oh, in the solution, okay, using hints in training. Yeah, using hints in training is basically you look at the correlation between 2 features, okay? Is it giving any unique information? Then add that as a, for example, we have x1, x2, x3. So I'll take a classic example. I'm not sure how many of you from network background, computer network background, or internet background. So source port, I have x1, x2, x3, okay. I have this source port, I have destination port, and source IP and destination IP. So for a video streaming, right? So video streaming, it's always between client source 1 and the client 1. And the source port and the destination port, if it's x1 and this is, sorry, I don't want to take x1. If it's 1, 2, 3 is a source port and the destination port is something like 3, 2, 1. And if there is a 1 traffic between 2 server and the client, it's always between 2 and 4, right? It's the acknowledgement and the data, acknowledgement and the data, right? So what I can do is, so I can see, I can find if there is a correlation between the source port and the destination port, correlation between the successive rows of the source port itself, and then add that as a correlation of source port and the destination port as a XY. So this one hint I can add, right? So you can look at the multiple hints. So using hints in training, it's pretty cliched answer. Okay. Obviously, all answers are cliched, but you know what I mean. So you can find some hints. Basically, if there's a correlation between these two features, giving some more unique thing, and then add that as a new, and then take a principal component analysis of all these features and add that as a x6 with a scale between 0 and 1 or something like that. So whether this gives some better accuracy. So that's why there is no free lunch. You just have to try. If it doesn't work, then remove this. That's all. Even if it doesn't work, just remove it. That's all. It's like that. You know what I mean? This is the best I can tell what hints mean. And there was another question: noise plus augmentation, and one more. What is one more? And don't we need to think of three? What is don't we need to think of three? Oh, you mean the using hints in training? That's the third. Oh, the question was asking for three. Okay. Oh, three options for improving robustness. Okay, that's why you were asking three. Okay, I missed it. My bad. Sorry. Yeah. So yeah, it's not just three. You can think of multiple things using hints in training. Principal component analysis, and what else you can add? Eigenvectorization, that's basically nothing but principal component analysis. A scaling, normalization. Normalization doesn't help when the data is less. Scaling can help. Scaling doesn't help again. Yes, that's a good question. PCA always improve robustness, and does it depend? Most of the cases, yes, it improves, but it improves when there is a discrete kind of problem. When there is a continuous kind of problem, for example, you are trying to predict rent value for coming month. That's a continuous value, right? In that case, it might work, it might not work. But when it is a classification problem, usually it works. So that's what PCA is always the first thing people try, if that helps or not, because in most of the cases, it gives a good result. So they just try the PCA as a first step and see if that's helping. But it necessarily not always works, but again, it depends. That's why in neural network, it's not easy to straight away tell this works. See, for example, if you take one particular problem, there are n number of ways to solve it. If you see the research papers, right? Okay, so that's related to neural network. I think I spend a good amount of time so that you guys don't have to reread the neural network part again. So I'll take lesser time for the unsupervised learning so that you can read again on the unsupervised learning. So any doubts regarding the neural network, or was it anything that I need to improve, or if I have missed anything? If everything is good, we'll go to, what is that? Unsupervised learning, the last one. Okay, that's great. Okay, so let's go to unsupervised learning questions. Okay, so the first question. Okay. First question: create by hand dendrogram for agglomerative hierarchical clustering. Okay, using each of the following conditions for the following set of 8 points. Okay, so we need to use the D max and then D min in the second case, and then we need to write a dendrogram. I'm not sure how they're going to test it in the final exam, but I don't know, should I spend more time on this? I'll just share the solution, share the screen. I'm pretty sure there was some issue in the solution given, so I just want to correct that as far as I remember based on. So they say create by, this is the question, right? So first we need to use the D max and then we need to use the D min. We need to write a dendrogram, right? Yeah, so this is the dendrogram. So these are the points. Points is sorted from the lowest to the highest. So from the first point, we name it as D1 successively. And then, so we take the distance, right? So distance, we basically take the max, right? So from the first to this, what is the, we take the distance, and the distance function, the formula is x minus the second point, and we take the absolute value, right? So the lowest is, so we take the distance, basically the distance between these 2 points is 1.4, and then since this is already there in the first cluster, we don't have to take the difference between these two, and then from here the next point is this, and the distance between them is 0.4. So these are near, so let's make them as a one cluster. So this indicates that these two are in the cluster, so we name that as a D9 cluster. And then since this is there, we just leave it and we take this. So this and this is almost greater than 1. So we can't make this cluster. So we just leave this and we go here. We take this. It's a 0.4, the distance. When we take 11.9 minus 12.3, that's 0.4, right? So this is these two are nearest. So we make those two in one cluster and we make it as D10. And obviously, this has already been taken in this cluster. We don't have to consider with this. So this is what in the first step we do it. In the second step, now we are with this cluster and we still have these points. So we take this. So here, right? Oh yeah, I think this is still correct. So D1 and D2, when we take it 1.4, these two goes into another cluster. And then this and this can go into the other cluster with 1.7. Those are the nearest comparatively. So this, you just sit it and calculate, you will come to know why we have taken these values, because those are the nearest ones. So from here, D2, so this forms the another cluster, right? And then we take this value and this. So in here, right? So we should take the maximum in this cluster, and in this cluster we should take, that gives the, those gives the maximum values, right? So if we take minus 5.5 and minus 2.6, these two gives us the maximum distance, right? So, but here they have given 2.5, but as far as I remember, there is some, so minus 5.5 plus 2.6, right? And that basically gives 2.1 or 2.9 or something, 2.9, right? Yeah, so 2.9. So that's just change that to 2.9 instead of 2.5. That's the only mistake in this, okay? And then same thing, we do the same thing even in this case. That gives to 3.5, which take 10.1 and 13.6. And then finally, minus 5.5 and 13.6, we take it on 19.1. So this is the final hierarchical clustering, right? Agglomerated. But we are taking max. But in the second term, in the second 1B, we take min. So we take my nearest in the clusters. So 0.4, 0.4, these are same, nothing much changed. But from here, we don't take the max. Instead, we take the min. So from this cluster, we take the min, that's -3 and minus, these are the minimum, right? So that forms with a 1.1 cluster. And here, this, like 12.3 and 13.6 gives the mean, that's 1.3. You know, you're getting the concept, right? So we take the min. So if we take it to the last, basically minus 2.6 and 10.1, right? These two from different clusters, but this is the minimum possible. So 2.6 and then this 10.1, that gives you 12.7, right? Distance, and this is the final cluster, right? So this is pretty easy, and we don't have to spend too much time on this particular question. So let's go to the question 2. This is very important question. Consider the application of the k-means clustering algorithm to the two-dimensional data set for c is equal to 2. If you remember in the last lab, I asked you to do for c is equal to 5 instead of c is equal to 2, right? Lab 4. So in this question, we are doing it for c is equal to 2 clusters, and these are the data. But in the lab, we have the data from the image that we have given, the pixel values, right? So here it's a two-dimensional value, x1 and x2 are the two features. What's the first question? The first question is using the Euclidean distance metric and initial means of mu1, so-and-so, mu2, so-and-so, compute the first 3 iterations of the k-means algorithm. Okay. And the B, do you expect the algorithm to converge at this point or continue? Okay. This is a very, very important question. Let me share the screen. So please keep your document so that I don't have to write the table always. But I think you'll be following it, okay? Or can I use the, I think I'll instead of I writing, I'll share the, because we don't have much time as well. It's already 8:30 and you guys probably might be bored as well. So if you take the solution, so this is the data given, right? X1, X2, X3, X4, XY. So these are the data given. And they have given the first random mean, that's 1, 3, and the second mean 0, -1. So likewise, we are supposed to choose 5 different means in the lab as well, right? So now what we need to do is we need to use a Euclidean distance between this mean and the data to calculate the distance, right? So between 1, 3 and -2, 3, with respect to the mean, we need to calculate the Euclidean distance, how far this particular data from this mean, okay? So 1 plus 2, that is 3 square, plus 0, that's root of 9, that's 3, right? You know how we are calculating the Euclidean distance, right? So distance between these 2 points is 3. Likewise, distance between this mean and the x2 is root 13, so on, so on, okay? The same thing with the cluster 2 as well. So now what we do is we need to see which the data is near to which mean. Is this particular data near to this particular mean? If so, then we put this data into the cluster 1. If it's near to the mean of the cluster 2, then we put that data to the cluster 2. So we check 3 and minus root of 20. So root of 20 is pretty bigger compared to 3, right? So 3 is a smaller distance. So which means x1 is near to cluster 1 compared to cluster 2. So we see it belongs to cluster 1, right? So same here. In this case, root 2 is lesser than root 13, so that we put to C2. Similarly, we perform all the clustering. So after the first iteration in the cluster 1, we have x1, x3, x4, and xy. And in the cluster 2, we have only 2 points, that's x2 and x6. Okay. So this is based on the random mean that we have taken it. But now we need to calculate the mean of this cluster. So we take 1/4 because we have 4 points, and we take the data values. X1 is -2,3, X3 is -1,2, X4 is 2,2, X5 is 4,1. And we just take the mean of this, -2, -1, 2, 4. That's 3, 3 divided by 4. Okay, that's 3 divided by 4. And then 3, 2, 2, that's 6, 7, 8, 9. Sorry, 8. 8 divided by 4, that is 2, right? So this is the new mean of the cluster 1. Likewise, the new mean of the cluster 2, that's 1 minus 1 by 2. Okay, now we need to calculate the Euclidean distance of all the data with respect to this new means. Okay, so means is now 3 by 4, 2, and then 1 by 2. We calculate the Euclidean distance. How do we calculate it? 3 by 4 plus 2 whole square plus 2 minus 3 whole square, and we have to take the square root of the whole thing. You're following it or confusing? Or should I write it on the OneNote? Following, right? Yeah, I don't have to write it on the OneNote. This is pretty easy, and there's nothing much to confuse. That's why I'm not writing it on the OneNote. So likewise, you calculate the Euclidean distance for all the cases and see whichever is greater. So 2.92 is always, obviously smaller than 4.6, right? So this particular X1 should be near to the cluster 1 instead of cluster 2. So this should belong to cluster 1. Likewise, we do the clustering, and so after the second iteration, we have new clusters where in the cluster 1, we have X1, X3, X4. And in the cluster 2, we have X2, X5, X6. Right? So now, if you see, X5 was in the cluster 1, but now it's moved to cluster 2. Right? Now we need to calculate the mean of this new cluster 1 and cluster 2, and you know how to calculate the mean because since we have 3 elements, it's 1 by 3, and we do the addition. Basically, we take the average mean, basically, right? So -1 by 3, 7 by 3, 2, 0 are the new mean, and this is the final iteration because we are asked to do the 3 iterations, right? And we do the same thing. And the class 1 and the class 2, it's the same thing. There's nothing changed. So it basically tells us that this already converged, right? Because there's nothing changed. So we don't have to go to do the next iteration because there's no change, right? Even we don't have to calculate this new means at all because there's no change in the iteration 2 and iteration 3, right? And then the second question, it asked whether it's converged at this point, or should we continue? We don't have to continue because there's no change in the clusters, right? Understood the second question? That's pretty important question. I think, yeah, you can be tested on that. So we'll go to the third question, right? So 2 alternative clustering algorithms. So if you remember, we used the k-means algorithm in this, right? So we took the Euclidean distance as a metric, and we performed the k-means algorithm. So here they are telling us 2 alternative clustering algorithms, which means they used one. So X1, X3, X4, right? So that, and X2, X5, X6, this basically second solution is a k-means clustering, right? That's what we got it based on the second problem. But they've used some other clustering algorithm, and they got X1, X3 as a D1 in the cluster 1, and in the second cluster they got it X2, X4, X5, X6. So they use the different clustering algorithm. So they have solution 1 and solution 2. Now they're asking us to find within and the between class parameter metrics for each cluster solutions for solution 1 and solution 2. You may use MATLAB to calculate the scatter matrices. However, you must show all the stages of the calculation. Yeah. So basically, we need to calculate within togetherness and the betweenness of the elements in the clusters for both the solutions. And then in the B, we need to calculate Kalan-Sky-Harvaz index to assess the quality of the cluster, right? So this is pretty important one. I'm not sure, should I write it? Or let me see. If you don't follow, just let me know. I'll switch to OneNote. Okay. So solution one, which is with this cluster one with x1 and x3. In the second cluster, they have x2, x4, xy, x6, right? So yeah. So the solution two is with the cluster one, x1, x3, x4, and the cluster two, x2, xy, x6. So we need to calculate the within and the betweenness, right? Togetherness and the betweenness of the elements in the clusters, right? So for that, this is SW within S, and SB is the betweenness, right? So SW, we need to take the summation for all the clusters, the SJ value. XJ is given as summation for each value with the mu j and the multiplication with the transpose of x minus mj, right? So since here we have two clusters, here j will be taking the value 1 and 2, that's all, right? So solution 1, d1, x1 and x3, d2, x2, x4, xy, x6. So mu1 is equal to basically the mu of the first one. So x1 is minus 2 and 3, x3 is minus 1 and 2. We just have to calculate the mu of basically mean of this particular cluster, and that is minus 3 by 2, 5 by 2. So why we are doing this, you will know. Basically, we are doing x minus mj, right? J here is 1. J can take value only 1 and 2 because we have only two clusters. So x minus m1 and then x2 minus m1, m2, right? Sorry, m1, right? X3. In this case, we have x1 and x3. So x1 minus m1, so minus 2, 3 minus this basically gives this value, and x3 minus m1. So this gives this. So now what we need to do is we need to take the transpose of each one and multiply and then add them to get the SJ, S1 and S2, right? So x1 minus m1, here it is, x1 minus m1, and then x1 minus m1 transpose plus x3 minus m1 multiplied by x3 minus m1 transpose. We just need to add this, right, to get the S1. So when we do that, we get 1 by 2 this value. And the similar thing, we need to do it for the second cluster, D2 cluster as well. So for that, what we need to do, we need to take the mean of this. So for that, x2, x4, xy, x6, x2, x4, xy, x6, take those and take the mean. So that is what the M2 is. And then we need to take x2 minus m2, x4 minus m2, x5 minus m2, x6 minus m2, right? And then we need to take the transpose as well and multiply them and add all those, and we get the S2. And S2 is this. And now we just need to add them to get the withinness of the cluster. And when we get it, this is what the withinness, and we need to take the trace. So addition of the diagonal elements, and that is 20, trace of SW. Why we need to take this trace is basically to calculate the Kalan-Sky-Harvaz index. So if you see, we are taking trace of SB and the trace of SW. That's why we are taking trace, right? So that's the trace of SW. And yeah, and then we have SB. SB is basically, we need to take the number of elements in the cluster, and we take MJ minus mu, and then MJ minus mu transpose. Okay. So yeah, here it is written. So here we are taking the mu for all the elements, right? So to check the betweenness. I'm not going the intuitive idea between this togetherness and withinness on Kalaska-Harbaz because we don't have much time, but I think you should be able to understand it. So we are taking the mean of all the data. So we have 6 elements, right? X1 to X6, and we take the mean of all, and then we come to know that this is what the mean. And then we calculate how far the cluster means from this particular mean, right? And how far they are. So that's what we are trying to calculate using the SP, right? And then we calculate M1, that's the mean one of this cluster. So that we calculated here, and then we calculate with M2 as well. So M1 minus M, that is this, M2 minus M is this. Now we just need to take a transpose of this, that's all. So NJ, how many elements are there in the cluster 1? We have only 2 elements, X1 and X3, right? So that's why just 2 multiplied by this M1 minus M multiplied by M1 minus M transpose plus in the D2 we have 4 elements, right? So we have 4 and then multiply this. So when you solve it, you get this. And if you take the trace, it's basically addition of these diagonal elements, and that's 21.67. We're gonna do the same thing for the second solution as well, that is D1 and D2, right? So we get the trace of SW, and then we take the trace of SB as well. So now we need to calculate how well the cluster quality is from solution 1 and the solution 2, and which one is better. So for that, the Kalinskaya-Harbaz index is what gonna help us. So that's basically trace of SB divided by trace of SW multiplied by N minus C divided by C minus 1. By the way, these formulas I think should be given, I guess. You don't have to memorize these, okay? But you just understand this. So N basically indicates number of data in the whole problem. So we have X6, right? That's the number of data. So that's why N is equal to 6. And C is how many number of clusters we have in a solution. In both the solution, we have 2 clusters, right? D1 and D2. If you see, so we just have 2 clusters, D1 and D2 in the solution 1 and D1 in the solution 2. We have D1 and D2. So this N minus C divided by C minus 1, they say it will go to 4 in both solutions. But trace SB divided by trace SW. So we got this based on the above calculations, and we get the 4.33, 2.58. So here they say solution 1 is better based on the CH value larger. So technically we identify that some algorithm that is used is better compared to the k-means algorithm what we used, right? So 4.33 indicates that, they say go to lecture 9, page 23 to understand. So basically what it tells us that, so clusters are tightly packed based on the mean. So that's what the Kalinskaya-Harbaz index tells us, right? Okay, so any doubts? Oh, most of the students dropped the tutorial. Okay, so let me know if you have any doubts, or else I think we are good to stop. By the way, is it okay if I stop the recording? But if you have any questions, so I'll answer those and then I'll stop the recording. The session was pretty. So initially when I started, I thought probably I would be winding it up so fast, but it took longer. But you guys understood? Or was it helpful? Okay, that's great. Okay, so if you have any doubts, let me know, or else I think I'll stop the recording.